Okay, good morning, everyone. Well, first of all, the check. Can you hear me?
Yes.
Yeah,
Great.
Yes.
Alrighty, then let us start with part two of this today's PULP training, which will be a more hands-on hands-on training than yesterday. Let me quickly jump through the schedule that we have planned for today. We will start with a quick introduction on the FPGA port of PULPIssimo, and I will highlight a couple of important differences between the normal RTL platform and the FPGA port, because it's important to know where to differ in order to be sure that we don't miss any crucial steps to test when we actually do a chip tape out. Then I will run through the most useful IPs or library of IPs that we have available on PULP platform on GitHub, and which ones we are gonna use for the training today. Um, this should not take more than, I guess, about 20 minutes to half an hour. The rest of the day will be pretty hands-on. So we will start with a longer exercise where you are asked to modify the memory layout of PULPIssimo or PULPSoc. So you will not only change the banking factor of the interleaved memory, you will also increase the memory size of each of those memory banks, and you will be guided through the steps to add an additional memory bank to the system, an additional private bank to the system. Um, Right now, it will just be an additional SRAMs, but the steps are more or less the same, regardless whether it's actually an SRAM that you try to add to the system or any other TCDM slave to PULPIssimo. Of course, another step of this exercise will be the modification of the linker script in order to benefit from the increased L2 memory size, as well as some modification to the linker script to map a particular section of your binary to the newly added private bank. We will, of course, guide you through the steps or give you an overview what the required steps are and prepared some more or less detailed instructions what you have to do step by step. Um, in the afternoon, we will do even more involved exercise, which will be the integration of a dummy IP that we prepared into PULP SoC. So not only will you see how you can wrap an arbitrary IP with a wrapper and wrap it with a memory mapped interface using OpenTitan's Reggen tool, we'll also see how you can easily leverage the IPs from the register interface repository on GitHub to quickly generate a AXI interfacing register file for arbitrary IPs, and how you can integrate that into PULP SoC and attach it to the AXI crossbar in the SOC interconnect. Okay, I saw that my camera froze again. Let me try to fix that. Okay, looks better. So the after integrating the AXI IP, you will of course also, there will be some steps where you are going to develop a small driver for that newly added IP in order to interact with the IP in software using the RISC-V core within PULP SoC. For all of this, we're not gonna do any hard-coded register address mapping. We will leverage the Reggen tool of OpenTitan not only to generate us the register file, but also to generate us the C header files for the hardware abstraction layer and leverage these C header files to create our own driver. Of course, the documentation that Reggen also generates is a nice addition, but we will not focus on that part in this exercise. This is pretty much the program of today. Both of these exercises will be rather involved and take 2 to 3 hours to complete. At least that's what we guess. Let's see who's fastest. And we will proceed with the same flow to ask for support as yesterday. You can jump to the PULP training Google Docs file. We will show you the link when it comes to the exercises again. And you can there enlist yourself in the support queue, and Robert and I, to the best of our abilities, will try to multiplex the support and try to help you in breakout rooms that we will create later on. Um, like yesterday, we will also update the little pulp trading website that we created and add additional material to it. I guess the most important parts are already there, which are the illustration of PULPIssimo and PULP SOC. The little schematics that we showed yesterday are already there. For the ones that asked, or actually for the ones that didn't ask but were asking themselves, the course slides and the recordings, I cannot make them available right now. I still have to discuss with Luca Benini on the modalities with whom I can share them, because he already voiced his reservations to just share it with everyone or making it publicly available. I don't think this should be much of an issue. Eventually I can share it with you. It's just that I can't share it right now. I guess that's pretty much it for the introduction. Do you have any question about the flow that we will use, or about the program of today? Or comments, something I forgot to mention, or yeah. No? Okay, then I will start with the first point on our schedule, which is a quick introduction to the PULP FPGA, PULPIssimo FPGA port. So for this, I quickly want to show you the folder structure of the FPGA port. I guess some of you will find it familiar, because it was the same structure is more or less also used for other PULP projects, not only PULPIssimo. Let me quickly navigate to it already, and now you should be able to see my screen. Yes. Alrighty. So here we are again in the top level of PULPIssimo, and in the FPGA folder is where everything interesting happens. And we see that we have a make file with some nice help text for the different targets that you can execute. And then there is a PULPIssimo subdirectory and a subdirectory for every single FPGA board that we support. The PULPIssimo subdirectory does not contain anything hard-coded or, actually checked in at all. So in the PULPIssimo/tickle folder, you will find all the scripts that ipabooks, the IP management tool that we were talking about yesterday afternoon, will auto-generate. So all of these scripts you find in here, they are used by the board-specific synthesis tickle files to add the necessary source files of PULPIssimo to the Vivado project. So you should not have to edit these files by hand. Editing the source files.yaml should be enough in order to generate the Vivado bitstream, the FPGA bitstream. As I mentioned yesterday, right now we are still using ipabooks for this. Eventually we will move to Bender as soon as we sorted out some of the issues in the flow. And but the setup will be more or less the same. There will be auto-generated tickle files in that directory or one of its subdirectories. The board-specific port-specific directories all have the same structure. They contain, again, a make file, which, let me check whether I actually documented it. Yeah, I documented it. So the make file will just start Vivado. I mean, the make all target will start Vivado and run the synthesis tickle script in the tickle directory, or here the run.tickle. This will be the one that started, that contains all of the interesting stuff to synthesize PULPIssimo and implement it in the FPGA. It will, as you can see, about here, yeah, here, it will source the auto-generated tickle scripts that IBM-Works created for us. So whenever you update the RTL or update the source files.yaml, you can just rerun the the generate scripts in the PULPIssimo root directory, and also your FPGA flow should be updated automatically. Besides the tickle script, there are a couple of other interesting subdirectories. So the IPs subdirectory contains all of the Xilinx IPs, which are synthesized as individual project before actually synthesizing PULPIssimo. So if we jump into that one, I have some slides on that later, but this just contains the different IPs that are instantiated and replace some of the behavioral modules we have within the simulation environment of PULPIssimo, like Xilinx Clock Manager that replaces the behavioral FLL model in PULPIssimo, the interleaved RAM memory macros, and the slow clock manager, which just generates a 32 kilohertz clock in case the crystal on the FPGA board is not already 32 kilohertz. The constraints folder contains all of the design constraints in XDC format. So there's not a lot going on here. Every board has its own XDC constraint, contains the timing constraints as well as the IO mapping for the particular FPGA board. Another pretty important file is the FPGA settings.make file. It is just a collection of variables, environment variables, which are supplied to the tickle script, to the synthesis tickle script, which contains specific settings for that particular FPGA board. For some FPGA board, it might be that the default clock period is too fast for it to be implementable, or that the interleaved or private bank size is too large. In that case, this is the file where you have to change the settings for the FPGA board. I know that's not the cleanest solution. Ideally, you would want a single source of truth where for example, the interleaved bank size of the RTL platform as well as the FPGA port are automatically in sync, but that's the way it is. I hope we can eventually fix that and make it in a manner where both RTL and the FPGA port use the same settings by default. But I mean, it's actually not that bad that you are able to override it on the board specific levels, although it's debatable whether that makes sense for the bank size of the memory. Yeah, I mean, let me check, are there any other important files in here? I guess that's pretty much it. In every board file, in every board-specific subdirectory, you will find a README, which will highlight the specifics of that particular port. For example, the Genesis board, it will tell you what default frequencies are, because I will highlight it again later on. The clock manager that I'm instantiating just outputs static default frequency. Unlike the behavioral PLL or FLL model in PULPIssimo, you cannot dynamically adjust the frequency. I mean, it's theoretically possible, but I didn't have the time and didn't see the reason for until now to write a protocol converter that converts between the custom FLL protocol we're using with the behavioral FLL and the protocol that the Xilinx clock managers use. Besides that, you will also see the mapping of peripherals to board, switches, buttons, and LEDs. And there should always be some indication how the reset line is mapped to the board, how you can connect with the UART, and how you are supposed to program the port. So some of the FPGA boards can make use of the integrated FTDI chips on the board and just use a different channel and program it without an additional JTAG port. Some other boards require you to hook up the JTAG lines manually to some PMOD header on the board. Genesis is a bit nicer in that regard, but it just reuses the same FTDI chip that you already use for the US micro USB connection that you already use to load the bit stream for the FPGA. Last part is for every board, there will be or should be an OpenOCD config file, which allows you to quickly, assuming that you use the programmer that should be mentioned in the README, it should allow you to easily start OpenOCD with the config file and connect with GDB to the OpenOCD TCP server, and you're able to load your ELF binary into the memory of the FPGA port, execute and debug your application like you normally do with GDB. That works pretty well, and it's also documented in the README. Okay, so back to the slides. Like yesterday, I prepared some illustrations how the different files in each of the board-specific directories interact with each other. I mean, I already mentioned most of them, so I'm not gonna go into the details. I will eventually upload this illustration also on the website in case someone's interested or needs some reference how the files interact with each other, but for now, I guess I will skip this part. So I guess one part in the directory that I forgot to show you is actually the RTL directory. Let me still go to that one. Genesis RTL, right? This is the only one I forgot. So the RTL directory in each of the Genesis boards contains wrapper for the technology specific, or I mean FPGA specific IPs that we are instantiating in PULPIssimo. Probably the most important one is Xilinx PULPIssimo, which is just a wrapper for PULPIssimo. The only reason why we have to again wrap PULPIssimo is that we need to instantiate this IO cell here that converts between differential clock inputs that some, or if not all, of the FPGA boards that we currently support have, and converts that to a single-ended reference clock. That's the only reason why we have this wrapper. And yeah, it attaches the relevant pads to the actual pads of the FPGA. The other wrappers you see here are just wrappers that wrap the Xilinx IP that we are generating with the, for example, this is a block-RAM macro that was generated as part of the make flow. And if we have a look again at the table, I can quickly go through all of them right now. So we have the pad functional xilinx.sv, which just wraps the IO buffer cells because we do not actually have IO pads like we do for the ASIC implementation. Maybe important to mention is that the boot ROM in the FPGA does not actually contain the boot ROM. If you want to do that, you have to do it yourself. For now, the FPGA boot ROM just contains a single hardwired instruction that you will receive regardless which address you try to access, which will always be jump and link to the same address you're currently at. So it will just trap the core in an infinite loop until the RISC-V debug unit takes over, preloads the memory, programs the entry point address, and enables the core once again. So no booting from flash using boot ROM as it is now, but it's not hard to replace that. You just actually instantiate a ROM or some large memory within the FPGA boot ROM wrapper. ClockN, I already mentioned. This is just a wrapper for the Xilinx clock managers, which generates the two different frequencies we have in PULP SoC. One is the SoC clock, and the other one is the peripheral clock. They are not at runtime configurable, as I mentioned before. This is also the reason why the PULP runtime has different config settings. So if we go to the runtime directory right now, PULP runtime, so far the only one of those config files that we sourced was the PULPIssimo.sh. However, there are also additional config files that you could source for PULPIssimo FPGA ports, one for every different port. The only reason why we need different settings for an FPGA port than for the RTL simulation is due to the fact that the clocks are not at runtime configurable. Normally, the PULP runtime would automatically try to program a default frequency for the FLL and work with the assumption that the peripheral clock runs at that particular frequency. However, for the FPGA port, not only are we not allowed to try to interact with the FLL, we can also no longer assume the peripheral clock to have a default frequency. So those different configuration file will tell the PULP runtime what is the default frequency for each of those FPGA ports. And the reason why that's important to know for the PULP runtime is because it will use that information to program the right clock divider settings into all of the IO peripherals. So if it doesn't know the right peripheral clock frequency, your UART baud rate will just be wrong because the clock divider setting will not be correct. Yeah, FPGA is low clock. That's just some detail. So for example, the Genesis board, if I remember correctly, has a 200 megahertz. I don't remember by heart anymore, but the Genesis 2 board certainly does not have the 32 kilohertz crystal directly attached. It has a much higher frequency, and we, however, need a 32 kilohertz reference clock for the timers inside. So the timers assume the presence of this 32 kilohertz clock. I mean, it's not strictly necessary, but it just makes a lot of sense because everything is written in the PULP RAM under the assumption that there is a 32 kilohertz clock. However, the reason why we're not using the default clock manager to do this is that at least the last time I checked, they had the limitations that you cannot go lower than 4.69 megahertz with the Xilinx clock manager from the input clock, at least for the Genesis board, which is why this particular wrapper not only instantiates the clock manager that generates a slower clock from the very fast input clock of the Genesis board, but also has a manually instantiated clock divider that actually divides the clock further down to 32 kilohertz. Okay, any questions on the FPGA port so far, or additions, comments? No? Well, in that case, just one last thing about the just a second. Just one last thing about the FPGA. Oh, well, there's not a lot to say in this on this slide. For those of you which are not familiar with that particular feature of Xilinx FPGAs and Vivado, in case you have to debug issues on the FPGA, or you want to debug an issue where you could benefit from the speed up of an FPGA when you compare it with RTL simulation, there is a really nice feature in Vivado that you can instantiate so-called ILA cores, in logic analyzer, I think is the abbreviation, that allow you to probe any internal signal of your design like you would with QuestaSim. Of course, it's not as direct as with QuestaSim. You have to open the elaborated design and you can select all of the signals that you want to have observable. And Vivado will run a quick re-implementation step where it will instantiate these in-logic analyzer cores in your design automatically. It's all GUI driven. You just click on the signal, you mark them for debug, and it can automatically generate those ILA cores for you. Once you regenerated the bit stream, this will allow you to watch the signals in your FPGA port as if it was as if there was a oscilloscope attached to it. So you can program trigger on the different signals. For example, you can program a trigger that will only capture the signal up to a certain buffer depth that you can program when the request address on the instruction fetch port matches a particular prefix. So the trigger conditions that you can program are fairly complex, or can be fairly complex, so you can really capture only the transactions that are interesting for you. So this feature helped me tremendously when porting PULPIssimo to the Genesis 2 board, and yeah, maybe it's also interesting for you if you're using the FPGA. One thing that I want to make you aware of, for at least for the Genesis 2 board, I know that at least in Vivado 2019, don't know the exact version, there was an issue that the default frequency that Vivado used when communicating with the Genesis board is quite high. It's, of course, quite fine if you just program a bit stream. Programming will be fast, verification will be fast. However, the really nasty thing is that the default JTAG frequency for the Genesis 2 board in Vivado is too high for the ELA cores to operate. So if you use the default frequency, the issue you will run into is that your ELA cores will just not respond. It looks like they are hanging or not working, and you don't really see an error message why that is, at least not an apparent error message that I'm aware of. So just to make you aware of it, if you're actually going to use that feature and the ELA cores just do not react, maybe try to lower the JTAG frequency in the hardware and natural Vivado. Okay, any questions on the FPGA port or additions to it?
Sorry, Manuel, I can ask you one thing about the script generator.
Yes.
Inside the PULPIssimo folder, all scripts are automatically created or not?
inside the PULPIssimo folder, everything is automatically generated. That's correct, yes.
Okay, and for example, in the PULPIssimo Genesis folder, we can write, we can modify manually the script, or?
Yes, nothing
Okay.
in the board-specific folders is auto-generated. You can modify everything however you seem fit. Only the part in the PULPIssimo folder, which is shared by all of the ports, is auto-generated, nothing else.
Okay. For example, if we want to add another EP of Xilinx, which is the better way to add inside the program, inside the project?
So the way that's currently handled is the following. For each Xilinx IP that you require in PULPIssimo, I have a subdirectory in the IPs directory of the specific port. And in each of those directories, there is a little makefile that actually creates the project. It's an individual project. It's not synthesized as part of the main project, and a small pickle script that does it for you. So, for example, this is, what did I just open? The Xilinx Clock Manager. So this will just create a new project with the name of the IP, Clock Manager.
Okay.
It will fetch the environment variables from the FPGA settings file that I mentioned before, right? It will have a look at those environment variables, and it will use those environment variables to set the property of this Xilinx Clock Wizard IP, right? With this create IP Clock Wizard from Xilinx, this is where I applied properties from the environment variables, and then I create an IP run, launch the synthesis, and then the project is fully synthesized. And as you can see in the top level make file of the board, of the Genesis board, there is one target for every IP, actually, clock and RAM. Yeah, there we are. So all clock IPs are compiled over here. And the target for PULPIssimo itself, and the all target, it's not the nicest way to do it, depends on the generation of those IPs. So when you run make all in the Genesis folder, it will first make each of the IP projects. And if you want an additional one, you just add a new folder to this IP. And of course, you will probably want to add a new wrapper to the RTL directory where you wrap that new IP and instantiate it somewhere in the PULPIssimo code base. Of course, it would be nice if the instantiating within the PULPIssimo code base was made in a manner where it's not extremely project specific or FPGA board specific. So if you can just replace one of the behavioral modules with your own version, then you probably just want to have an override. So your wrapper in the RTL directory will just override the file that would be part of the normal RTL simulation flow. And yeah, this way you could get around using a lot of if-defs in the PULP SoC code, which conditionally include one or the other module. I know currently that's not the way it's handled. That's for legacy reasons, but ideally the RTL code should not make a distinction between FPGA port and basic port, and it's just a matter of which files you compile and in which order you compile them, whether you end up with Xilinx IP or behavioral models, or in case of ASIC synthesis with the actual wrappers for the black box macros.
Okay, thanks, man.
You're welcome. Okay, so then let me start with the next topic, which is the IP landscape we have in PULP. So I will quickly go through all of, not all of them, but over 3 main repositories that are used most often if you develop something with PULP. So the first and probably the most important one for tape outs is the text cells repository. If we quickly navigate to this one on GitHub, do I have a new browser somewhere? So, text cells generic. Okay, so this is the repository I'm currently talking about, the text cells generic repository. So this repository actually contains technology, contains generic wrappers or behavioral descriptions of technology-dependent cells. A prime example of such a cell, maybe like this you can read it better, would be clock gates. And I mean, for power optimization, your clock gates are most likely manually instantiated. However, there are quite a couple of manually instantiated clock gates in PULPIssimo. Some of them are for power saving reasons, but other clock gates are actually there for the correct behavior of some I/O peripherals. So, for example, you would have a clock gate in the I2C peripheral that conditionally gates the peripheral clock and allows it to pass to the I2C clock pad or not, depending on whether there is a transaction ongoing or not. So, I mean, there are some more. I will show them to you in a minute. But the important thing to note is that if you are actually doing a tape out or an FPGA port, those technology specific cells, which in the text cells generic repository are just behaviorally described, need to be replaced with the cells of your particular technology. So if you're doing a TSMC 65 tape out, you would have to replace all of the cells used within the designs with the cells from your standard cell library. So you would look up which standard cell you want to use for clock gating, and you would replace the cell in your technology specific version of the text cells generic repository. So if I can quickly show you that, it's probably easier to understand if I just show you. I guess let's do that this way. Do I have it here? I think I should. I think I should have this list, but yeah, no. So awesome, yes, there it is. So, well, this actually doesn't make a lot of sense. This I probably added for a previous training. So normally the pulp SoC would depend. Let me show you the pulp SoC IPs list. So YAML PULPIssimo would depend on the text cells generic somewhere over here. So this one is instantiating the generic description of the technology specific cells. So for example, the clock gate in the generic version is just a well, actually the clock gate is not that bad because this clock gate actually uses the ledge style clock gate, which is perfectly fine. It's just a bit larger and probably rise and fall time is not optimal, but this would actually work. However, you see that for the clock AND gate, this is just using normal binary operation between the two clocks, which of course is not, I mean, is not optimal. So for your particular technology, you probably want to, I mean, not probably, you most certainly want to replace all of those cells with something technology specific. And the way you can do that is by, let me switch back to this one over here. So ignore this part here. So you remember PULPIssimo depends on the TextCell's generic repository. What you can do now is you can generate your own copy of the TextCell's generic repository, your own fork of it, which is what I did here. And within that fork, you just replace the files or the content of the modules with instantiations of the actual clocks, of the actual standard cells. For example, this clock delay module, I call the module exactly the same as in the generic version. So if we go back to the TextCell's generic, so this is the generic version. PULP clock gate, or what was it called? TL. True, deprecated PULP clock gate. Guess in here. PULP clock delay. There it is. Yeah. So you see, this is for sure not synthesizable. We are using a delay statement for 300 picoseconds. And yeah, that just doesn't work. And in the technology specific version, I call the module exactly the same. However, within the module, I instantiate the standard cells I want to use for that particular technology. And after creating my own version of the TextCell's repository, what I can do is I can probably, I didn't do that in here, but what you could do is, and would be the correct solution to do it, is to add a ipslist.yaml to the technology specific TextCells, and in here you would depend on TextCells generic. So this probably I think it's commit, right? Commit, and then just whatever version. 2.2. I don't know what version I actually should use, but let's assume that it's this one. So the reason why the technology specific cells should depend on the generic version is not because I'm instantiating the generic cells within my technology specific cells, but to enforce the correct compilation ordering. If my technology specific cells depend on the TextCell's generic, I can be sure that IPAPROX as well as Bender, for Bender you can do the similar approach, will first compile all of the technology agnostic, the generic cells, and only for synthesis, because my source files.yaml should contain some skip synthesis flag. Well, actually, it should be called skip, not skip synthesis, skip simulation, of course. So only for synthesis, in synopsis, for example, the technology agnostic cells, the generic cells, will be overridden because we are recompiling modules with the same name with the technology specific cells. So with this approach, depending on the generic cells, we can be sure that the compilation ordering will override the generic version with the technology specific version for synthesis only. And after generating such a repository, I just add it as a top level dependency of the whole project, like this. Okay, I hope that was more or less clear. Otherwise, please interrupt me. Good. Then, yeah, I guess I talked long enough about the text cells. I just want to mention a few of the cells that are available as part of this repository. There are generic SRAMs. There are clock AND gates, glitch-free clock gates, programmable delays, clock XOR gates. Yeah, nothing special about this. So if you need some of these cells, that's where you would look for them, and that's the cells you would have to replace in your own tape out, because some of them are actually instantiated in PULP SoC, so they need to be replaced for a tape out. Common cells. So the common cells repository, again on GitHub, would contains high-level modules. Show you that contains high-level modules that are should be technology independent and are used a lot and fairly useful for your own development of IPs. It also contains a couple of Verilog macros, which can be useful for the declaration of registers of a certain kind, and some assertion macros that are commonly used. So this little illustration gives you a quick overview on the different parts that the common cell, or the different IPs that the common cell has. On one side, we have simple clock dividers, integer clock dividers, and reset synchronizers. We also have clock domain crossings. These are used fairly often in PULP SoC. So different kinds of clock domain crossing IPs like breakouting FIFOs, two-phase handshaking IPs, or also some IP for metastability, or getting rid of metastability with serial synchronizers. I mean, those are not hard to implement yourself, but still they're there. Then you have delta counters and linear feedback shift registers in case you need some, well, delta counters, obvious LFSRs. These are just pseudo-random number generators. Are fairly useful sometimes, for example, when you do random arbitration. We have data path elements. The address encoder or address decoder I want to highlight specifically because this is an IP that's used a lot in the new SoC interconnect that's currently in, or that I was talking about yesterday, and also used a lot in the Oxy IPs. And it's just an address decoder that accepts some address mapping rules. So you have different output port. The address decoder will just decode the address and generate a select signal for some demultiplexer, for example, or a multiplexer. Well, error correcting decoders, encoders, leading zero counters, gray to binary, binary to gray converter, just some stuff that's useful for a lot of things. Then the common cells IP also contains some data structure IPs like FIFOs, behavioral SRAMs, and counting Bloom filters are probably not as important for you, I guess. Then Oxy IPs, that's another repository, and for this I just want to quickly point you to the right IP, because we're going to use that one later on anyway, or the right repository, I must say. So here we have the Oxy repository, which contains the new generation of Oxy IPs. I mean, not so new anymore, but these are the ones that should be used for all new designs. We have still a couple of legacy IPs around in the underneath PULP platform, and some of them are still used within PULP cluster. In PULP SoC, I'm quite certain there is no legacy Oxy IP. I replaced them, but in PULP cluster there are still some legacy ones, but you probably should only use the ones in this repository unless you have a very good reason not to. A lot of them are fairly well documented and they follow a really good coding style, in my opinion. So I can only highly recommend, if you need any sort of Oxy 4 Lite or Stream IP, have a look at this repository. It not only contains a crossbar fully connected crossbar for AXI. It also contains commonly used ingredients for any kind of AXI IP you might need, like multiplexers, demultiplexers with converters, pipeline registers for AXI. Clock domain crossings are important as well, and other stuff like protocol converters from, I guess, only two APB, oxylite, and yeah, atomics filters. Okay, any questions on the PULP IP landscapes about the text cells I was talking about, or common cells, or any additions to what I said so far?
How to
I'm sorry, Thomas, I think we can't hear you.
Sorry, that was by mistake. My headset died and it, sorry.
No worries. I guess that was no question. Alrighty, then let's proceed with the very first exercise. So for this, I mean, what you already did yesterday, I guess, was clone the PULP training SW repository, which contains all of the exercise files. We added a lot of changes since yesterday, so please, if you didn't clone it yet, you can just clone it. If you already did clone it, please run a git pull on it in order to update your repository to the latest version and in order to have all the updated exercise instruction. So for the very first exercise, we will focus on we will start with the mem layout exercise. So you'll have to switch to this particular directory, and the README instruction, the README markdown file within that directory should contain all the instructions you need. Regardless, I will quickly introduce what this exercise is about by showing it to you on GitHub training. Let's see. Mem layout, README, there it is. So these are the instructions. In this exercise, you are required to change the memory layout of PULPIssimo. So the original layout, actually the formatting is not that nice. Well, that's why you probably shouldn't edit stuff at 2 o'clock in the morning, but regardless. So this is the original layout of PULPIssimo. You have 4 128 kilobyte banks for the interleaved memory. I think actually it's a bit less than that in the current version of PULPIssimo, but it doesn't make a difference. And you have 2 32 kilobyte private banks for the core. Your task will be to increase the amount of interleaved memory from 512 kilobytes to 2 megabytes by increasing the banking factor to 8 and increasing the size of each bank to 256 kilobytes. This will be the one of the hardware modification steps. The other one will be to add a new private SRAM bank to the system with as well 32 kilobytes. I will quickly just go through the steps just to give you some overview what you will be required to do. We will start with the modification of the interleaved RAM layout, where we will change the relevant parameters, or in this case a macro, in order to change the banking factor of the system. Then, yeah, well, it shouldn't say increase the size of each bank. I accidentally wrote decrease. I'm sorry for that. Increase the size of each bank to 8,192 32 kilobit words. And we are also required to change the relevant settings as well in the FPGA settings.make file of every board, of every FPGA board. because as I already mentioned, the RTL and the settings for the FPGA ports are not automatically in sync. You have to do that manually. Then, of course, we will increase the address space for the interconnect so we can be sure that our transactions to the increased amount of memory still are routed to the right location. In the second step, we will add an additional SRAM bank where we will again define a new memory region for the bank, and we will instantiate the bank at the right place within PULP SoC, and as well modify the SoC interconnect to have an additional port and to apply the right address rule to the parametric interconnect so our transactions to the new memory region starting at this particular address are routed to the right location, to our new port. So right now in PULPIssimo, that's the way it looks. We have 3 ports on the contiguous logarithmic interconnect. Your task will be to add a 4th one, port with port index 3, and add the additional address rule that specify which memory region should be mapped or routed to port index 4, which you will add. Yeah, I guess if you did both of these changes, it will just be adding an additional wiring signal between the interconnect and the wrapper of the SRAM banks, and debugging the stuff. I mean, debugging in the sense right now to just build it and see where you did coding mistakes, syntax errors, or just stuff that breaks during elaboration. Then in the second step, you will modify the linker script where you will extend the size of the L2 memory to where you increase the size of the L2 memory so the linker can actually place more data into that region without stopping with a linker error. Yeah, then you will add a new memory region for the new private bank, and you will map one of the sections of your ELF binary to that new memory bank. Of course, all of this modification requires some testing, whether it actually works. So we prepared some test application. One application in the link test subdirectory is just there for compilation. So you're not actually required to run that application. You will only have to check with readelf or some other tool like the NM tool to check whether your symbol in that little test application are mapped to the right memory addresses, and whether the linker was able to place a huge array into the L2 memory, an array that would be too large for the original PULPIssimo system to fit into L2. So if you didn't modify the linker script, you would get a linker error because it doesn't fit. Then there is a second application subdirectory, the memtest subdirectory, which just does some very, very basic tests, whether you succeeded to add the new private bank and whether you succeeded adding new interleaved memories to the system, or additional memory banks to the interleaved region by just writing to some memory locations and reading back from them. This is an application that you're supposed to run, and please use the GUI mode in order to debug when stuff goes wrong. We also have added some instruction what signals might be of interest to have a look at if stuff doesn't work. I guess that's more or less it about the exercise. Of course, the procedure will be the same as yesterday. You will join a breakout room of your choice. In case you need help or have questions, open the Google Docs sheet. Again, for the ones that were not able to join yesterday, I will quickly show it to you. This is the Google Docs file. Where is it? There we are. This is the Google Docs sheet. You just enter the breakout room number you're currently at. You enter your username, and Robert or me will, as soon as we are available, join your breakout room and try to solve your issues or help you with questions. Yeah, I guess the exercise README should be pretty self-explanatory, but still, well, actually, I didn't add it to the slide yet. Yes, I did. In case you want to have a look at the illustrations about the SoC architecture we showed yesterday, please visit the following website. You will also find the link on the Google Docs. So if you just type in this address, you will find the link clickable without typing it yourself in the Google Docs sheet. And this little web page will contain, let me show you, contains illustrations, the illustrations we showed yesterday about the PULP SoC. And I mean, it contains some frequently asked questions. We try to update this section live while we are helping you and debugging your issues. So yeah, maybe you can from time to time update the page and see whether your particular problem was already addressed and added to the exercise website. Okay, any questions on the flow? If not, then we will proceed as follows. I will now open the breakout rooms. And since this is a rather involved exercise, and please do not hesitate to ask if you feel stuck or lost, you will have time until the afternoon to solve it. We will have a quick discussion on the exercise in the afternoon at 13:15. I will add that to the slides for the people that will join later so they can see when we will resume. But yeah, so we will open the breakout rooms now. You have until 13:15. At some point, probably around 12 o'clock, we will also take a lunch break, and we will resume at 13:15 with the discussion of the exercise and the introduction of the second larger exercise of the PULP training day 2. Any open questions left? If not, then let me open the breakout rooms, and I hope you will enjoy the exercise. So just for the recording, I will recapitulate what I just did. So we did, I just did the first step of the memory layout exercise, which is the increasing the banking factor of the interleaved region from 4 to 8. And to do that, I switch to the PULP subdefines and change the value of the NBL2 channels from 4 to 8. Okay, next step is to increase the size of each bank to 65,536 words. And we need to do that in 2 places. One is the L2 bank size over here. Some of you might have noticed that the 2 values, the one in PULP soc and the one in L2 RAM multibank, are not identical. This is just a stupid inconsistency. They should actually be the same. This is for a legacy reason. There used to be SRAMs that were smaller, and part of it was standard cell memory, but yeah, it doesn't make any difference from a behavioral point of view, because this value that's smaller is just used over here, right? One line below. That's the only reason it's used, and it is to calculate the memory address width that we need to actually address the whole memory space of a single bank. And yeah, that's only some performance improvement for the micro-DMA. It's not actually used to determine the size of the banks. That's happening in L2 RAM multi-bank over here. So let me increase that value to 65,536 and the same over here. Right. So now we effectively increased the banking factor by 2, and we increased the size of each bank by a factor of 2. Now, as I mentioned, step number 3, we have to still do the manual synchronization between the settings of the FPGA ports. Again, I'm using some, so I'm going to use some editor food to do this. I'll switch to the FPGA PULPIssimo Genesis 2 directory and just open one of the FPGA settings. I know, of course, that there is one of these FPGA settings file in every single port, right? There will be one in Nexus, one for the set board, one for the Nexus video board, but yeah, I'm gonna do some search and replace magic right now. So let me increase this value over here to 65,536, because that's what determines the size of the block memory that is instantiated in the FPGA port of PULPIssimo. So I'm going to do that right now. So let me search in all files for that particular string, and let's batch edit them. 65,536 like this, and we save it back to all files, and now all of them should be up to date. Okay, now next step, step number 4, modify the address space for the L2 memory region. I mean, it's one thing to increase the size of the SRAM banks and increase the number of banks, but we also need to make sure that the SOC interconnect actually knows about the increased size of the memory space, so it still routes all the transaction to the right ports, to the right location. And to do that, there is only one step required. Since we're not changing the actual number of ports to the SOC interconnect yet, we will do that later. We are only increasing the memory region, and the memory regions in PULPIssimo are all defined in a single place, which is in top level of PULPIssimo. RTL includes SOC memmap. This one over here. Here, all the memory regions are defined. Some of you might have asked themselves, what is the alias for? This is a legacy thing. It's actually no longer present in the latest version of PULP SoC, which was updated, I think, 4 or 5 days ago. This is just a legacy thing. You can safely ignore it for the sake of this exercise. The only relevant things are those 2 lines. So the start address, of course, stays the same. However, if you use our trusty calculator, where is my calculator? Speed crunch, there it is. So if we use my trusty calculator, let's do some calculations. We see that the difference between 10 between the start and the end address converted to kilobytes is 512, right? So let's actually increase that, and again, let's do it like this. We have the start address, of course. I mean, if you're using a different calculator, these steps might be a bit more involved, but with this is why I pretty like this calculator pretty much for the purposes of an electrical engineer. So I can just add 2 megabyte, actually mebibyte, and this is the end address that we need, 1C21000. So let me copy that guy and paste. Like this. Okay, so now we updated the memory region for the interleaved memory as well. I guess that's pretty much it for increasing the size of the interleaved region, increasing the banking factor. That's all you need. Now, second part.
Manu, 1 second.
Yes.
Don't you now have overlapping memory regions there?
Do I? Where?
Down there with the private bank.
No. No.
Oh no, sorry.
No,
I didn't do that right.
you're perfectly right, Georg. If that was the case, that would be dangerous. Always make sure that the memory regions you define here are non-overlapping. This is the single source of truth about the global memory space of PULP SoC with the new interconnect. If the stuff is not overlapping here, you are perfectly fine. Of course, then it still depends how you map stuff. For example, in the peripheral region down here, this is for the APB slaves. Those ones are actually defined in another header file. This one, I think peripheral bus defines these ones. Right here, you have all the start and end address for the different APB peripherals. So you have to make sure those overlap. Those also don't overlap. But for the global scale, for the SOC interconnects concern, this is the place where you define all the memory regions. And yes, you have to make sure they don't overlap. Yeah, in case I go too fast or you have questions, please just interrupt me. So any questions on step 1, changing the interleaved memory regions size?
I got another one.
Yep.
What's the reason for the FPGA port's memory, like the bank size being defined in that script there?
Good question. So, I mean, this is a trade-off how you want to do it. Since I'm using the flow that the IPs, the Xilinx IPs are all compiled in different projects, I need some way to specify the values with which I want to parameterize the Xilinx IPs with the create IP flow. Maybe there are different solutions that better fit our needs, where you would have a single source of truth, but that was just a design decision that kind of relates to the way that I think the Hero platform already did it. I had a look at Hero and some other FPGA ports when creating the PULPIssimo FPGA ports. I know it's not an ideal solution, but it's more or less an arbitrary decision.
Okay, so just one comment is you can actually take this from the RTL because the Xilinx, the Vivado compiler, can infer memories. So you can just instantiate a behavioral SRAM there, and it'll make you a block RAM, and if it in any size you want.
That would have been a better solution. You're right. Yeah, should have thought about that one, but yeah, that's the way it is right now. I just wanted to have it consistent with the other Xilinx IP because I'm pretty sure you cannot infer a PLL from RTL, and we need clock wizards as well in the PULPIssimo. But yeah, maybe that's worth thinking about. Maybe having changing that one. But as of now, that's the way it is. Any other comment or question on changing the interleaved memory region size? If not, I will directly proceed with the next step, that is adding a new additional private SRAM bank. And the very first step, for the very first step, we are already at the right place. That is adding a new memory region to the SOC mem map for our new private bank. So let's do that. Put that one over here, define SOC mem map. Let's call it exercise bank start address. And so we said the start address should be 1B00 and 000. And since the size is 32 kilobytes as well, like the other banks, I already know what the offset is. So this should become an 8. And analog to this one, right? This private bank 0 is also 32 kilobytes, so this one has to have offset here, offset 8 as well. Now change that to end address, nicer alignment, and now we defined a new memory region. We just defined the start and end address. We actually have to also change the sock interconnect rep to use those macro defines. It's not done by just adding a new define here, obviously. But first, let's go to step 2, that is instantiating a new private bank in L2RAM multibank. So let's go there. L2RAM multibank over here. I'll generate some tags here. C tags. Okay, there we are. So now I am in file IPs PULPsock RTL PULPsock L2 RAM multibank. This file over here. And wait, what did I change here? Oh yeah, I increased the size. So next step, let's start by adding a new parameter here for a private bank number 2, same size. And yeah, we probably also need that guy here for a private bank number 2, using the size of the private bank number 2. I mean, they're all the same size, I know, but if you wanted to change one of them and you had them all linked together, it would be just messier to clean it up. So why not just do it the clean way if they are independent private banks anyway? Yeah, I said that, of course, I could increase that guy to 3 and have a third port. But for the sake of this exercise, I want to create a dedicated port, just cause. There's no particular reason, except that if you do it that way, it more closely matches the steps that you have to take for the next exercise that we're going to start in a couple of minutes. So slave additional slave. And yeah, I saw some of you had something like this. Since it's an array of, since it's only a single slave, I don't actually need an array. Okay. Then if we scroll down through this file, we see that those lines here relate to generating interleaved memories. We don't have to touch them. We already took care of it. It's parametric, nothing to change here. However, that's a different story for the private banks. You see, each of them is individually instantiated. So I probably should copy everything that relates to one of the two and just change the signal names. So let's copy private bank 1. So we see here in the beginning, there is some stuff that takes care of TCDM handshaking, like reflecting the grant signal. This is just because the SRAMs, of course, do not speak the TCDM protocol. So with those couple of small assignments, we take care of having the SRAMs behave like they spoke the TCDM protocol. That's just what these lines are doing. Then we have instantiation of the generic memory and the private RAM for the FPGA port. Again, this is not the cleanest solution, I know, but that's what was already there. So let's do that. We call this guy additional bank exercise. And of course, we should change all of this mem prislave stuff to our, what did we call it? I think something additional prislave, exactly. So again, I'm using some editor magic to do this because I'm too lazy to do all of this by hand. Just take a couple of minutes more if you had to do it manually, but still I'm too lazy for that. So additional prislave like this. So this is done. Now let's go through each line to make sure I didn't miss anything. So these two lines are responsible to remove an offset in the address. Let's suppose the a start address of your private bank was not aligned to the natural boundary of the SRAM bank size, you would have to subtract the start address to remove the offset and have the addresses that you supply to your SRAMs actually start at address 0. That's why we're doing this part, and obviously I have to change that one to private address 2, this guy as well. 2, then I should change this guy here to sock mainnet exercise and start address like this, and address width, this should also be changed to private bank 2 address width, this one as well, this one as well, and same, oh, important one, I keep forgetting that one. The instance name has to be adjusted as well, otherwise we will run into elaboration errors later on, or actually compile errors. So let's change that to, and this guy, let's change it to number 2 as well, and this one as well. Okay, now I really hope I didn't forget anything. In case someone sees something I did wrong, please yell. But I guess that's all about it for instantiating an additional private bank in the L2 RAM multi-bank wrapper module. Any question on that part? I guess silence means no. Then let's continue with the modification of the sock interconnect wrap, which is step number 3. So this is a bit more involved step, or probably the most complicated one of the steps for what concerns hardware integration. So let me switch to the sock interconnect wrap. So this guy here. So as it says in the exercise steps, the first thing to do is to add a new dedicated port to the sock interconnect wrap. So I want to have an additional port down here. Again, I know I could increase the number of private slaves and just increase the error size, but we're not going to do that for this exercise. So let me switch to that file. Again, all of those files I'm editing right now are in the RTL PULP sock directory within the PULP sock IP. Okay, so let's switch to the port list. We need an additional port. Let's call it SPAR TCDM master. Well, just something, yeah, additional, yeah, why not the same name? Something like this. And what next do we have to do? Yeah, now we come to the address rules. Actually, if we strictly go by the instructions on the of the exercise, next step would be to increase the number of contiguous slave ports in the parametric interconnect from 3 to 4. So maybe let me quickly show you the exercise sheet again. So just for you to be reminded, the private banks are attached here, and this is the contiguous region, the contiguous crossbar, and it now has 3 ports. We want the 4th one to attach the 3rd private bank to it. So let me do that. So where is it? Contiguous slave port. So this is the wiring signal. This is the signal that actually goes into the parametric interconnect, this guy down here. So we can tell it that we need a 4th contiguous port, not only 3, now we need 4. Maybe it's good practice to also update the README or the comments right next to it. One for exercise, private bank And so this parameter relates to the size of the contiguous slaves, this one here. And as you can see, I'm attaching a system Verilog interface array to this particular port, which is defined up here. So obviously, I also have to increase the size of this interface array by 1. So now, as we can see here, we probably should also assign the input port. I think we called it additional price slave, right? Additional price slave. So I should assign the input port to the system Verilog interface array. I know I could do this manually and assign each and every individual signal to it. So it's doing something like this: additional price slave request equals contiguous slaves 3.request, and so on and so forth. But then, first of all, the code will explode because I mean the code size just increases unnecessarily. It's extremely verbose, and you can be damn sure that you will do mistakes like this. So it's better to use a macro. And if you do a mistake in the macro, everything will be wrong or everything will be correct, unless you're extremely creative in writing your TCDM assign macro. So this is just some preprocessor magic, which does the assignment for me. So additional price slave, assign it to contiguous slaves, port number 3. So now we attached our additional private slave port to the SoC interconnect. What remains in step 3 is to modify the address rules of the interconnect. So let me once again show you the illustration. So what we have is we not only have, well, let me start this way. If a transaction comes from a master, there are 2 steps or 2 decision points where it's decided where the transaction ends up in order for it to reach our new private bank, which should be here. So first, we need to add an address rule for the TCDM demultiplexer to tell it that our new private bank memory region should be mapped to port 1, this port here. So in the address rules of this particular block, if we scroll up a bit, so these are the TCDM demux address rules. You see that both private banks, I mean, this is just a shorthand, those actually include both private banks that are already existing, and the boot ROM memory region are both mapped to port index 1, which is the middle one over here. So we just have to add an additional rule here that our new private bank region should also be mapped to port 1 of the TCDM demultiplexer, the red guy here. Let me quickly do that. Copy that guy here. Port 1 start address is stock nmap. Then what did I call it? Private additional or exercise? Yeah, exercise private bank, exactly. This and sock nmap exercise private bank and address. And also be careful, now our parameter of address rules, this guy here, has 5 elements, which means we also have to increase the local parameter up here by 1, since now there are 5 address rules within that array. So we took care of routing our transaction to this region. The next step would be to tell the contiguous log interconnect how to route the transaction to the private bank port that we added, which would be port number 3. I hope so, right? Port number 3, did I change? Yeah. Additional private slave is attached to port number 3. So let's add third rule to the contiguous crossbar, actually a fourth rule. So we increase that by 1. And let's add another rule down here. So we want to route it to port number 3, the one that we added. So we increase the index to 3, and the memory region we want to map there is soft map exercise bank start, and the end address of the region is exercise bank end address. As you can see up here, these are just mapping rules. You can have multiple regions, distinct regions mapped to the same port. It's perfectly legal. Of course, you have to take care that the addresses that arrive to the SRAMs are actually reasonable, but these are just routing rules through the SoC interconnect. I guess these were all the steps that we needed to route our transaction to the new private bank. The last step is in PULP SoC. We need to wire our new port. So I just created this port here. You need to remember the additional price slave port. We need to wire that one and connect it to the new port we added for the to the L2 RAM multibank module. So let's assume there is a new signal as an exercise that push like this. Of course, this signal doesn't exist yet. I have to instantiate it. So let me do that, maybe at the same location where this guy is defined, which is up here. Of course, in the same file. So let's define a new wiring system Verilog interface instances min exercise bus like this. You see this guy is already connected to the SOC interconnect rep. The other side should be the L2 RAM multibank, which should be somewhere in this file over here. And I guess I called it the same. RAM multibank, let me check. Solving mem layout. I called it additional price slave over here. And yeah, as min exercise bus. Okay, these were all the 5 steps that you needed in order to modify the SoC interconnect and add a third private banks. Any questions on this part? No questions? I guess since we are, well, let me check. Are we? Yeah, we are a little bit short on time. That's why I will skip the actual simulation of it. But for now, let me just try to build it and see whether at least that one succeeds. Projects of so I didn't add any new files to the project. I didn't change any dependencies. So in theory, it should not be necessary to regenerate the tickle scripts, right? It doesn't hurt to do it regardless, but should not be necessary. All it takes is to build the project once again. I mean, it's most safe if you clean the project before you build it. It should recognize it if you change one file and only conditionally rebuild that particular library. But I know that for some corner cases, when you add new files, new folders to the include path, that doesn't work. So safest option, just clean it before you build it. Let's hope I don't have any errors. Yes, of course I do. No, this is the error of me using the Quistasim version 2020. I have to quickly change the tickle script for the optimization. Tickle files, TLG opt. This should do the trick. And 0 errors, 22 warnings, just what you should have seen as well if you were able to solve the exercise. Okay, I skipped simulation because you're a bit short of time. If you actually managed to make it build and actually went through all of these steps, chances are quite high that it actually works in the end, because if you messed up some of the steps, you most likely would end up with elaboration errors or even compilation errors. Any question on the hardware part of the exercise? Now's the time. If not, I will hand over to Georg.
Robert.
Sorry, to Robert to explain you the second part of the exercise, which is adjusting the linker script. You ready?
Yes.
All right, then let's switch over to Robert.
Okay, so now since we have changed the memory layout, we have to also tell the compiler and the linker about this new setup. And we do this by adjusting the linker script. Okay, our task is to first adapt the L2 memory region to match the new size of the new interleaved region, so that actually the compiler knows that it can put more data into the L2, more instructions into the L2. Then we add a new memory region for the third private bank. So that is a new memory region because it is not it is discontinuous. It is it doesn't you can it does it has a separate memory address space. And finally, to show that we can map sections to this new private bank, we will try to map the BSS section to it, and then inspect like the resulting binary to see if we manage to do so. And finally, we also have a link test program that you're only supposed to compile and link, which will check if you actually manage to do these steps. Okay, so first we extend the L2 memory region. So this is I'm here in the mem layout exercise folder, in the link test folder. And well, if we just now try to build the link test.c, let me do this for custom installation purpose. You will see it will fail with a linker error. And this is because in the link test.c, which we try to compile, we instantiate a huge array, and it's so large that it does not fit in the L2, in the size of the old L2 memory. So we have to tell now the compiler, hey, we actually have more memory available, please use it. Okay, so your task now was to find out where's the linker script and what do we have to change. And let me show this. So we go to the we go to my training folder where I have my PULP runtime. And inside PULP runtime, I will now search for the linker script. I know the linker scripts, they end with an LD postfix. So I just search for LD. And we see, okay, in the kernel /chips/PULPIssimo/link LD, we have the linker script, which is probably for PULPIssimo. Okay, and now, yesterday I told you what this what these parts of the linked script mean. And for what now concerns the size of the L2, we have to edit this memory section. We can see that the memory section starts at 1C0000 as we expect, but the length is wrong for our purposes. Okay, so let's figure out what kind of size we need. Actually, I did the calculation just before. So 2 kilobytes is actually 200,000 in hex. 2 megabytes is actually 200,000 in hex. So let me just edit this to 200,000. Okay. Actually, someone remarked that it's a bit more than 2 megabytes because it's 2 megabytes plus 64 kilobytes. So we could also consider those additional 64 kilobytes to correctly match the total size. And let's see if we can figure out how much. Can I show crash? Why is that? Okay. Okay, it's 10,000. I didn't remember. Okay. So let's change this to 10,000. So this is now 2 megabytes plus 64 kilobytes. Okay. So now if we compile our program, we expect now to not have a linker error anymore since we adjusted the size of the L2. So let's do this. Okay, we could successfully link our program. So this was the first part of the exercise. Now the next part of the exercise is to add a new memory region for the third private bank. So let's go back to our linked script again. And here we just need to add a statement that refers to this new memory region. So I call it priv3 in my linked script. We tell him about where the where it starts, the address of this new private bank, and it is given in the exercise. I think this is in the exercise. We see it is 1BB000, which I put here. And finally, as for the length, I believe it is 32 kilobytes. Okay, which is what is it again? It is 8,000 in hex. Okay. Okay, now we have our third private bank declared in our linked script. So now our linked script knows about it. And finally, to prove to have kind of like a proof that we can put now stuff into this private bank, the exercise was to map the BSS section into it. Okay, so let me search for the BSS section. Okay. So remember how these statements work. On the right side, we have the sections generated by the compiler, and on the top, we have the name of the output section. And on the bottom, the arrow points where this output section is being mapped. So what we have to do here, we just have to tell him, hey, please map this to our newly defined memory region. So now we expect the BSS section to be mapped to priv3. In order to show that this works, let's recompile our link test program. Okay, we have compiled it, and in the exercise, it tells you please use either nm or readelf or something like this to show that you actually map the symbols that would end up in BSS, that these map to the memory region of the private bank, of the new private bank. Maybe a short comment. When we go to the link test program, when you look at the link test program, you see that I declared two variables, my static var BSS0 and my static var BSS1, and it is defined by the C standard that static variables in file scope, they always are automatically initialized to 0. And it turns out that in the ELF file has a section called BSS, which is supposed to be always 0. So that is why the compiler will always put these kind of variables into the BSS section. So in order now to show that actually the BSS, that we can put variable, that our BSS section is now mapped to the private bank 0, we can just observe these variables in the binary to see if they have these addresses. On another note, I have done this weird stuff down here, where I read a volatile variable into my static var BSS and so on, and print it out. This is just to trick the compiler that it doesn't remove my variable, because it would not, if it's unused and it's dead code, and the dead code elimination pass of the compiler will just remove it. Okay, so now let me compile. Let me now just compile before. Let me show you that actually we have something in the BSS section. So I use readelf for this normally. So I use readelf -a. -a is just show all information, and I read this link test executable, type it into less. Okay, and now let me search for my static variable. Okay, we see I have these two, my static variable BSS0. If you look on the left side, you can see it is mapped to 1B00. We know this is the private, this is the new memory region which we have defined in the private bank. You can also see number 14 here in this column, this MDX column, and this, you can match this to the section headers here, up here. So you can look at 14 and you see this is the BSS section. This is the same information. Okay. Maybe a few things I often like to do is, let me show, you can dump the data which is put into a section with object dump. So I often like to do something like object dump, what is it, minus, I think, yeah, -s, -j, and then you can give the name of the section, for example, data, and it will dump the contents of the data section. In our case, there's not much in there.
Sorry. Sorry for that.
Okay. You could say, hey, what about the BSS section? But if you try to dump the BSS section, it will be nothing, because the BSS section is it is empty, because it's only implicitly filled with zeros. Okay, that about object dump. What did I want to say too? Finally, you can make custom sections if you want to. So you can use the GCC attributes to map data in custom sections. So it's something like GCC attributes section, new section or something, and then you can put this in front of your variable declaration. So my variable, something like this. Okay, now I have to play tricks again, because let me see. Let me make an array or something, and let me printf this array. So this is again just to trick the compiler, basically, in so that it doesn't think that I don't use this variable. Okay, let me recompile the program. Let me do another readelf on it. Can you see my var? Okay, it is now mapped into the global section again. Yeah, okay, we also need to tell the link. No, actually, let me see. Yeah, the compiler is removing the section because, now it's here, okay. So, yeah, so I put now this new section and, well, you can use it to group together. You can put in the data or functions or whatever you want, but often it's not something you want. But for example, let's say, often for like assembly code, for example, vector interrupt table, you do make a custom section for it, or for example, sometimes you have a custom section called small BSS or small data, where you put very small data, and then you can play tricks with the global pointer to access the small data with fewer instructions. Okay, that's it. So this was a small excursion. Also, what you can do with sections, but the exercise was really only about doing these few things, like meaning and extending the L2, size, and mapping something into new memory region which you defined. Okay.
So
Robert, sorry.
Yes.
Sorry, I did not understand one thing in the linker script. Originally, the origin of L2 was 1C000 blah blah 4. But why was it starting at 4?
Oh, okay. Yes, yes. This question came up a few times. So the thing is that in PULPIssimo, we have some aliasing set up. I call it mirroring, where certain address ranges are also mapped to this address. And it turns out that this address here, the 1C000000, is also when you write to 0, then you also write to this address. So let's, for example, yes. So the 0 address is also mapped into this address, and this is quite kind of bad because the 0 address in the C programming language has a special meaning. So you don't want to make this like you don't want the compiler to put something there. That's
okay, thanks, got it. Yeah,
it's a quirk of PULPIssimo, of the PULP platform, that we have this mirroring setup. Yeah, the 0 address is just banned.
But is it a feature or it's like a hardware bug?
No, it's a feature because it's like this, that in RISC-V you can always put a 12-bit immediate, right? And when you load and store from addresses around 0, then you can do it in a single cycle. Otherwise, you would need to do like load upper immediate and then load word with this 12-bit offset. So in short, this was an optimization where it allows you to access the lower 2 kilobytes with a single cycle.
Okay, I see. Okay, thank you.
And that means this 0 page is basically mapped to 1C00 as a mirror. But this is actually not a very good idea, because there's also the global pointer which you can use for this kind of stuff. You can place a global pointer into your. That's what you normally do. You have a global pointer. You point it into your small BSS in your small data section, and then you can also do single cycle access for everything that is put in the small data section. This is the normal way. This one is basically a small hack to gain to shave off.
Double the, okay, yeah, understood, got it.
Thank you. it's not very. I mean, it makes many things a bit more annoying, debugging and so on.
But so this is also something that also the PULP compiler must know, right?
Yes, in the PULP compiler there is an attribute called tiny. So yeah, it's called tiny. And when you use the attribute tiny, then it will map it there.
Okay, perfect. Yeah, but it's a really a clever idea.
Yeah, but
anyway,
don't use it.
Yeah. Okay. Thank you.
Don't use it.
Thank you.
Okay.
Okay. Any other question on this exercise? If not, then I guess we will proceed with the next exercise, the second one of today, and which will be about the integration of a custom IP into PULP SoC. So what you will do as part of this exercise is, I mean, we actually, well, the slide says you are going to write a memory map description of the IP in HJSON. Actually, we already did that for you as part of the exercise files that we prepared, but still you are supposed to have a look at the file. So if you remember from the topics we discussed yesterday, Robert showed you this tool from Low Risk from the Untitled project called RecGen, which allows you to describe register files in a very concise way using this HJSON format. And the RecGen tool allows you to easily generate register files from that description, generate the hardware abstraction layer C headers for the registers that you defined, and also generate documentation. So this is what this RecGen tool will do for you, and this will be also one part of the exercise. So maybe it's actually easier if instead on the slide I quickly go through the task description on GitHub. So let me open that for you. Where are we? Over here. So for this exercise, the steps are a bit more involved, but still we will try our best. So there we are. This is again in the SW directory or repository that contains all the exercises. And the one we are having a look at right now is the full stack IP integration. And as the instruction says, you will have enough time to go through that by yourself later on. We prepared a little stupid dummy IP. I can show it to you that this little dummy IP is over here. Let's see. Yeah, there it is. The dummy IP is called Wide Alu, and yeah, well, we call it accelerator or sometimes de-accelerator because it's actually slower than doing it in software. But this little dummy IP is a hardware accelerator which is supposed to perform mathematic operations, addition, subtraction, multiplication, as well as some binary operations on very wide words. So in this particular parameterization, I mean, it's a hard-coded value. You shouldn't change it, otherwise some stuff breaks in the exercise. We use operands which have a bit width of 256 bits. Of course, the output of the binary operations, if you do a multiplication, is in that case 512 bits. And yeah, this stupid little IP has a couple of input signals. It's quite a custom interface, nothing really standardized. The purpose of this IP is to show you how you can easily wrap arbitrary IPs with a wrapper which has a memory mapped interface with AXI or APB using the RecGen tool. Now, still talking about this wide ALU IP, it has a couple of input signals. It has trigger signals, which starts an operation as soon as this trigger signal is asserted for one cycle. It has two input operands of the 256-bit input width results. it has, as is already also described in the exercise sheets, this deacceleration factor, which is just a fancy name for a configurable delay. With these signals, you can configure how many cycles you want to wait before you receive the result. It's not like this is a really useful feature, but we just wanted to create an IP which has a number of different input signals and which will show you most kinds of signals that you might encounter when having a memory mapped IP or when having a custom IP that you want to memory map. Yeah, I mean, it's not terribly important for you to understand the IP in detail. It helps a bit if you do, but for the sake of this exercise, you will just be wrapping this IP in a wrapper that you develop on your own. You will instantiate in this wrapper not only the IP itself, but the auto-generated register file, as well as protocol converters from the register interface repository. Let me quickly open that one for you. So PULP platform register interface. I mean, this is a bit of a strange name. So register interface is just a repository that contains IPs around a really simple custom protocol called generic register interface. So this is a protocol. It has a very simple set of signals, and it's much simpler to use than UXI or APB. But the nice thing about this protocol is that the patched version of the Recgen tool that we use at ETH, the one that was patched by a number of PhD students from our groups, those are the guys, is that they patched the Recgen tool to expose such a generic register interface at the boundary of the register file. And this repository contains a number of protocol converters from UXI to this particular interface and from APB to this particular interface. So it's really easy to wrap your own IP with a memory mapped interface with either UXI Lite, UXI, or APB. You just instantiate the right protocol converter and you hook up the signals for the generic register interface with the generated register file generated by the Recgen tool. Those steps are described in way more detail on the actual exercise description, but yeah, just to give you a quick overview what the steps will be that you're going to do. Then after wrapping our IP and having a new top-level module that exposes an UXI interface to the memory mapped white ALU IP, we will then proceed to integrate this IP into PULP SoC, modifying the SoC interconnect rep in a quite similar fashion that you just did for the previous exercise. And then that's pretty much it. You will have custom IP integrated in PULP SoC, attached to the UXI crossbar that's already present in the SoC interconnect, and you can access it from any bus master within PULP SoC. Most importantly, the fabric controller. So the RISC-V core will be able to access the IP through its memory mapped interface, and through normal reads and writes from the right addresses that you will define as part of the exercises, you can control and read from this particular IP. Of course, the exact addresses where you need to write and read from are not handled by hand. This is what we do with this HJSON description using the Recgen tool. So you will have a look at this anyways, but I will quickly show you. So this is the HJSON register file description for our IP. We define the name of the IP and we define the width of the registers, 32-bit, and maybe this line is important, bus device. Like this means we want our register file that's auto-generated to use this generic register interface. Where is it? Oh, register interface, right? So this protocol, if you specify something else, you might end up with a different protocol, most likely the tile link protocol that low risk is using. But we want to use this generic register interface, and that's what this line is doing over here. And in here we specify all of our registers, and the register file, the Recgen tool will take care of generating a nice address to register mapping automatically for us. We just need to tell it the base address, and all our registers that we specify here will be in increasing order, starting from the base address that we will specify later on. Yeah, so much about the integration. So that's pretty much it about integrating the OXI IP into PULPISimo. In a second step, that's why we call it full stack integration, you will use the auto-generated hardware abstraction layer header files and combine them with a driver that you will develop or partially develop. The bulk is already done for you. To interact in an easy manner with that wide ALU IP. So we don't want to have our main application that tests whether the stuff works to have hundreds of different hard-coded memory addresses. We want to have a driver that takes care of this for us. And the driver should leverage the auto-generated header files. So that's what we are going to do in this step. You will complete the driver. You are required to integrate the driver into the PULP runtime in the same manner that Robert showed you on the first day. And then that's pretty much it. You will finish with a small main program. I guess we provided that as well. Yes, there it is. So you're provided with this little sample application, main.c, which does nothing more than triggering a operation on the wide ALU IP, in that particular case, a multiplication with 256-bit inputs. Yeah, I know we're only using the very first 32-bit, but it doesn't really matter. So we are triggering this operation and we show the result. This will be the test, and if you managed to integrate your IP in PULPISimo and finished implementing the driver, well, you should see the result of this operation, which will be 3 times 5, 15. Okay. So are there any questions on the actual exercise? The steps are described in a little bit more detail than I just did, but I just want to give you an overview of what you're supposed to do and what is going to await you. So any questions on this? If not, I guess we will do the same thing we did for the previous exercise. So I'll switch again to the exercise slide. So yeah, again, you're supposed to have the SW repository with the exercise files cloned or pulled to make it up to date. Guess you already did that, and switch to the full stack IP integration subdirectory and have a look at the GitHub README. I know for the previous exercise, we noticed some mistakes in the README. So yeah, in case that happens again for this particular exercise, please open the GitHub page with the README in your browser and occasionally refresh the page in case we have to push changes to the instructions while we were doing the exercise. Again, you can join a breakout room of your choice. And yeah, now the question, how long do you have time for this? I guess so we have 2:30 right now. I mean, about 3 hours. I guess should be, well, should be enough. It's not an easy exercise. I agree with that. But yeah, let's try to meet again at, we have now, so 5:30. So we will wrap it up at 5:30. This will be the end of this 2-day PULP training. So we'll quickly discuss the exercise again at 5:30. I guess we won't have time to solve it in front of you at that point, but we can show you the sample solution and discuss the remaining issues that you might have encountered. And yeah, that's pretty much it about the exercise. So I will now open the breakout rooms once again, and same procedure as previously. Please include yourself in the Google Docs sheet you see on this page. If you have any questions or you require support, please also occasionally check the FAQ on the PULP training website we created over here, right? You also find the link to this website in the Google Docs sheet if you didn't notice that so far. So yeah, occasionally check the FAQ page, also refresh it because we will be live updating it while we are handling your support requests. Okay, that's pretty much it. Any questions on the procedure? Well, if not, then I'm gonna open the breakout rooms now and yeah, enjoy the exercise. After this longer exercise, I will quickly go through the solution. We don't really have the time to solve everything in front of you, but nonetheless, I want to go quickly through all the steps in the instructions and show how the solution could look like. Just to make sure that you understood what the necessary steps are. I'm perfectly aware that this exercise is probably not that easy to solve in only 3 hours. I mean, after all, it's the integration of a complete IP into an SoC, and yeah, that's not a task that's supposed to be easily solvable in just a couple of hours, but yeah, nonetheless, I want to show you what the basic steps are. So let me maybe switch again to the instruction page. Yeah, let's open a new web page over here. Start and let's stack integration. And now you should see my screen, I guess. Okay. Then, so we start with step number 1. Yeah, I mean, we already discussed that one. It was just to familiarize yourself with the wide auto IP. So this IP that we provide you, which does those wide operations on wide operands, 256-bit operands. In part 2, you were supposed to, in instruction number 2, you were supposed to go through the HJSON file, this file over here, and just get an idea what's going on there. If you were to wrap your or integrate your own IP into PULP SoC, you would have to write this specification yourself. But yeah, given the limited amount of time we have available for such a training, yeah, you would, if you were to do that yourself, you would go on the OpenTitan. Actually, you cannot see it if it's on the other screen. There it is. So you would just go on OpenTitan's website and check the documentation of the Recgen HJSON format and just implement or write the HJSON accordingly. Probably looking at some of the IPs that OpenTitan provides, because all of those IP come with their own HJSON and they make an excellent example on how to do things. Then the next step, create a new GitHub repository with the files of this directory. So the files of this exercise directory, full stack IP integration. I went ahead and did that in my own GitHub namespace. So GitHub Mickey, and we see what I did over here. Where is it? The wide alu IP. There it is. This is the little repository I created. It contains, of course, all the files that we provided, the alu.hjson, the wide alu.sv file, the package that we provide, and the newly developed top level that I will show you in a minute. An important aspect is that it also contains the generated system verilog code directly in the Git history. If you were to integrate an IP in a more professional manner, and if you had more than just a couple of hours to do it, I mean, that's normally something that can easily spend a week or more doing it, you would probably generate make targets that regenerate the auto-generated register file as well as the package whenever you check out the IP with ipapooks or Bandit or whatever IP tool you are using. But for the sake of simplicity, I directly committed the auto-generated files to the Git history. Yeah, for this exercise, it should be fine doing it like this. So now let me well, maybe let me jump back to the instructions. So because we did part number 1 and 2, part number 3 would be to also generate the source files.yaml and an IPs list.yaml description file for our wide alu IP. So let me show you the ones that I added over here. So the source files.yaml, of course, it contains the references to the 3 files, actually 2 files that we already provide you, the wide alu package and the wide alu.sv. Those 2 files are generated by the RecGAN tool, but of course I need to add them to the wide alu as well. And this is the new top level wrapper file that we added. The vlog options, the -l flag, we need it because we make use of a package in the register interface repository. And as mentioned yesterday, if you need a package from a different repository, you need to add this -l flag. If it's just a submodule, you don't need it. Then a couple of include directories. Well, again, the ugly hack, these include directories are not actually within the scope of this wide alu IP. They are outside of it in IP's register interface. But yeah, since everything is cloned as a subdirectory of IPs, that kind of works, although it's a little bit of an ugly hack. So this is the source files.yaml, the IPs list.yaml. Yeah, might be that it's not quite complete. I just wrote that a couple of minutes ago. So we have the AXI IP, since we are using IPs from the AXI repository, and we need IPs from the register interface repository. But I just realized before, when I tried to update and build everything, is that there is a version conflict. So let me quickly resolve that one. So PULPISimo also requires the register interface. However, it uses this particular commit ID instead of a branch name. So let me replace that with the same commit. So now they are aligned, so no more version conflicts. Okay, so since I just changed an IPs list.yaml file, I have to push the changes for them to take effect. Version of register interface. And let's push them to origin master. Now that asks me for my password. And there we are. Okay, now it's online. So we are at we're done with step number 3. I know that I'm skimming through this extremely fast, but that's probably the only way we can have some kind of wrap up of the exercise that's on recording that you can maybe consult. If you try the exercise at a later time, then you will take more time, will take the time you need to study how the things actually interact with each other, and maybe use this recording as a reference, and then it might make a bit more sense. But still, if you have any questions, feel free to interrupt them. So step number 3, we created the new GitHub repository, and we are now at step 4, where we were supposed to write a wrapper for our wide ALU IP and add it to the directory, to the same repository. So let me show you this wrapper and maybe explain once again what the role of this wrapper is supposed to be. The wrapper, this guy here, wide ALU top, has only one interesting interface. I mean, of course, it has the clock, reset, and test signal, and only one interesting interface, which is an AXI slave interface, this guy here. It also has the parameters, but yeah, doesn't really make much of a difference. And now this wide ALU top consists of 3 main components. Component 1, most obvious, it instantiates the wide ALU IP, the IP we actually want to wrap, obviously. Second component, it instantiates the auto-generated register file. So this is the module that's auto-generated by the Reitgen tool, and that's where it is, wide ALU at top. This huge file is completely auto-generated by Reitgen, so I don't really need to care how it works. It's just a register file with some address decoding logic that complies with the specification in the HJSON file. So this is the second component. Obviously, the register file needs to be somehow connected with the wide ALU. Yeah, I notice I'm going in reverse order in what the instructions were saying, but it doesn't matter that much. So the register file connects with the wide ALU IP. And yeah, well, actually, no, it makes more sense if I start from the input of the top level module. So the input of the top level is this AXI slave bus. However, the auto-generated wide ALU register file doesn't speak AXI. It uses this generic register interface protocol that I mentioned in the afternoon. And we thus need a protocol converter from the register interface repository. So this is the third component of the module, the protocol converter from AXI to generic register interface. So we have the AXI slave that comes in, it goes into the protocol converter, and out comes a signal of type RegBus. RegBus, this is the system Verilog interface for the generic register interface. That's the name of that interface, RegBus. So this comes out of the register file, and now comes the ugly part, the conversion between system Verilog and system Verilog interfaces and system Verilog structs. I'm well aware that this part is not that nice to understand if you're not well versed in using, for example, the AXI IPs from the AXI repository. They use this style extensively, but for the others, this might look very unfamiliar. And I can only suggest you to, if you are actually trying to integrate your own IP, take the time to go through the macro definitions and see what they are actually doing. It's not rocket science at all. It just looks a bit weird. And I will quickly try to explain what the individual lines do. And maybe at a later point, when you had more time to wrap your mind around, my explanations might make more sense. So since we are dealing with system Verilog structs, there is an important difference between system Verilog structs and system Verilog interfaces. interfaces can be parameterized. You can supply an interface with parameters like address width or data width and have an interface with those exact specification, similar to a module which you can parameterize. Structs, on the other hand, they are a one-way ticket. You declare the struct for a particular width of the addresses or the data, and that's it. If you need a struct with a different width, too bad. You have to declare a new one. Now, if you don't want to do this declaration yourself, this is where those macros come into the picture. The macros help you in that way, in that they declare a new struct with the right address and data width. What the macro expects is that you supply it with a type definition for the address. So I tell my macro over here, hey, the address width of the struct that I want to declare is of this size. So this is a normal system Verilog type, that same as in C, right? I tell it, hey, logic with a logic array of this particular size is supposed to be called address T. This is one of the parameters for the macro. The other one would be a declaration of how wide the data bus should be, this part here. And the strobe signal, well, we don't make much use of it, but the strobe signal would, in theory, allow you to access individual bytes of your generic register interface. Doesn't really matter. So now what these two lines do is they declare two different structs with the name reg request T. I could call them whatever I want. My reg and my reg response, and this is somehow translated to something like type def struct and then a lot of blah 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 for the register interface, and in the end it's called reg response T, and I think inside it will do something like address T address, and I think, is it comma or is it semicolon? Comma, yeah, and then data T data. Yeah, I'm just skimming through it so you get the idea. So this macro just declares a new struct with this particular name, and it uses the address type and the data type that we declared up here in order to generate the struct with the right width. Yeah, since system Verilog structs can only be used to connect modules in one direction, we need two of them, one in the direction from the register file to our IP, to the ywip, and for the other direction. So the result signal or the status signal, it travels the other direction. It goes from the ywip and goes to the register file. Yeah, so you need two structs, one for the request side and one for the response side. These are the two structs that are going to do that. Then this is just a declaration of the struct. Now we need the actual wiring signals. That's the next two lines. These two lines declare the wiring signal with the type of that struct. Actually, since I renamed my structs up here, I should change that here as well. My reg request type. So now we have two signals with the type of our freshly declared struct up here. So let me change that back, since the rest of the module still assumes that the types are called reg request type. Last two line of the ugly system Verilog macro hackery is this part here. This is doing the actual conversion between system Verilog interface and the structs. If we actually had a look at the macro definition, it would make a bit more sense what this guy is doing. Maybe let's do that. I can only encourage you to have a look at the macros. It helps a lot understanding what's going on. It should be in the include, I guess, register interface, assign. or here. So we are using this guy, recurse assigned to request. That's this part. So what does it do? It assigns the values from the right-hand side to the left-hand side. So this is just shorthand notation for a struct assignment. Yeah, just assigning every signal from the interface to every field of the struct. Okay, after this rather complicated explanation, let's proceed. So what did we do so far? We converted our AXI slave signal or bus with the protocol converter to a register interface bus or interface, register interface, system Verilog interface, and we used some macro magic to convert it to structs. Those are the two struct signals that we used. One signal for the connection from the register file, from the AXI to register file protocol converter, and one for the other direction, from the register file to the protocol converter. Next, we actually instantiate the register file and we hook it up. So we use those two signals, those two struct signals, and we actually attach the wiring signals we declared up here to the ports of our auto-generated register file. As you can imagine, the wide ALU register top also needs to be aware of our newly defined structs, our newly declared structs, which is why wide ALU top has two type parameters. So be aware of that. Wide ALU top, these two, those are not your normal parameters that you see most often. The key difference is this keyword type. So this is not a parameter that expects some integer value or some string or whatever parameter you're using. This is actually a type. So the default is logic. It doesn't make any sense, but yeah, we just want the default value. And we are supplying our freshly declared struct types to those two type parameters. Okay, final step, we instantiate the ywip and connect the wiring signals from the register file to our wide ALU. The wiring signals are declared up here, over here. Again, those are structs, one for the direction to the IP and one for the other direction. Everything that needs to leave the IP and go into the register file is in this struct. Both of these are part of the auto-generated system Verilog package. That's why I'm gonna import it up here. And if we open it quickly, we see it here. Wide in the generated system Verilog code package. You scroll down here, you see that the Regiga tool automatically generated two structs for us. One that connects the register file and for the signals that need to flow from the register file to our custom IP, and one for the other direction. And as you can see, this is just a packed struct which contains a field for every register that we declared in the HJSON. So we have the operand A register, we have the control 1 and control 2 register. Those fields actually relate to the HJSON. Right, control 1, control 2, and we have the status register and we have the operand registers up here. They're automatically generated by the to these structs. Within each of those register structs, we'll find declarations of the individual bit fields. So for example, the control one register, if we had a look at it again over here, has two fields. One field is the trigger field, which is bit number 0, and the other field is the clear error field. And we see those were translated over here by Recgen automatically. We have the trigger field and we have the clear error field. If you want to figure out more about what those Q and QE signals mean, yeah, maybe have a look at the OpenTitan Recgen tool documentation. It's just Q stands for output of the flip-flop, like we have it in the style guide that we call our state holding elements. We always generate a signal state underscore D and state underscore Q. This is the same. This is what comes out of the flip-flop in the register file. And for the other direction, this is what goes into the flip-flop of the register file. That's why it's in the hardware to register struct. Okay, so to reiterate, our wrapper instantiates the custom IP. It connects it with the auto-generated register file, and it converts the generic register interface protocol to AXI, so we can expose just a single AXI slave port at the top level. Any questions about the wrapper?
Yes, in the definition of the AXI to reg, what is that decouple W?
In the definition of the, which one?
In the parameters of AXI to reg.
AXI to this one, or?
No, the instance.
No,
Or
Yeah.
what the parameters are.
Just decouple W.
Ooh, actually, I don't know by heart. I would have to check the documentation. I guess this will instantiate some additional flip-flops in the data path to decouple maybe read and write port from each other. I'm not 100% sure, but I guess something in that sense. Pretty sure it's documented in the IP itself, right? AXI source wrong, it's in the register interface. Source AXI to reg, let's check, is it written? It is. Whether the AXI write channel should be decoupled with register. This can help break long paths. So if you put this guy to 1, it might improve your timing at the expense of some additional latency, I'd guess.
I see. Thanks.
Other questions? No? Well, then let's proceed with the actual integration. The integration is pretty much identical to the steps we did for the integration of the additional memory banks. So let me quickly open the PULP over here, and let's open the instructions once again. So yeah, we went through all of those steps up till here. Yeah, so we should commit the changes. Well, I obviously already did that, push the changes, and we should now instantiate our wide alu top in the top level of PULPsock. So let me show you how I did this. So PULPsock, somewhere in here, there is the wide alu top over here. I just added it right after the sock interconnect. It doesn't really matter where you instantiate it. Well, it uses the SOC clock and the SOC reset signal, because that's what all of the IPs in the SOC domain are using. So same clock as the interconnect, same reset as the interconnect, and yeah, well, the test mode we just added, we don't really make use of it. Then we need a wiring signal, or a wiring interface that connects our wide alu top module with the interconnect. course, we will have to modify the interconnect as well, but let's start with the wiring signal. Let's see where I did that. So you see here are a lot of different wiring signals at the top, more or less at the top of PULP SoC. And we declare a new instance of an Oxybus with a particular address width. I mean, I'm making use of some of the already pre-declared parameters, but it's also fine if you just declared them as 32 and 32 for the data width. The only thing that's more important is that you use the right Oxy ID output width. It probably would go a bit beyond what I can explain still as part of this training, but the important thing to note is that the Oxy ID is not only has the role of, well, let me phrase it differently. The Oxy crossbar appends a couple of additional bits to the Oxy ID signal that allows backrouting of the responses. If you want to know more about what the Oxy ID is actually used for, you would have to have a look at the Oxy specification. The important thing to note is that it is very, very important that the ID is big enough so you do not cut away the additional bits that the crossbar appends to the ID that would allow backrouting. Otherwise, you end up with really, really weird errors. The errors will look like you have a request that leaves the crossbar, you have a response that enters the crossbar, but the response never arrives at the master port. The reason for that 99% of the times is because your Oxy ID width is too small and you cut away the important backrouting information bits. Okay, never mind about that part. So we have this bus signal, we attached it to the YW bus, and now of course we need to connect it to the sock interconnect wrapper. You see, that's what I did here. Obviously, we also added a new port to sock interconnect wrap. So let me open that guy right now, sock interconnect wrap, and we see there is a new port, the YW slave port. And we did the same thing as we did for the additional private memory bank. We add an additional, well, first we connected this additional port to the interface array that connects to the parametric interconnect. So we reparameterized the sock interconnect to have, instead of only 2 Oxy slave ports, we need 3 Oxy slave ports. We see the Oxy slaves, that's this signal here, which is an array, and we increase the size of this array from, originally it was 2, we increased that to 3. And same as we did for the private banks, right? That's what we did in the morning over here. We connect the YW slave to the array of Oxy slave ports. And we add an additional address rule. So in PULPIssimo top level, again in the includes sock memmap, we added a new start and end address, a new region. I'm not sure I actually used the one that I described in the instructions, but it shouldn't make much of a difference. Just assume that I used the same start address that I wrote in the instructions. If I didn't, yeah, well, I actually did, so it should be 4, right? 4 and 4. And yeah, you defined the new memory region, and now we add a third address rule for the Oxy crossbar. So the YW start address, everything between YW start and end address is supposed to be mapped to port 2, to which we just now connected the YW slave down here. There is one tiny detail that's important. Well, it doesn't make, nothing will go wrong if you still add it, but you don't need a demuxing rule for the L2 demultiplexer. If we have a look again at the, let me open the exercise, documentation, illustrations. Where's the sub interconnect? There it is. So I mentioned that only briefly yesterday, but whenever a transaction doesn't match any of the address rules we specified for the L2 demultiplexer, it is by default routed to port 0. So we don't need a rule for the L2 demultiplexer. If it doesn't match this address region, or this address region, it is automatically ending up in the AXI crossbar. So the only rule we really need is the additional rule for the crossbar itself. That's this one over here. With those two steps, I guess I didn't forget anything, right? Yeah, those are the steps to actually integrate the PULP SoC. Now, a little bit ugly part is about actually integrating the ywip with IP's list into the project. That's a bit of a git commit push nightmare until it actually works. But what you should actually do are two things. First, you already generated the repository with the ywip inside of it. And you also need to fork PULP SoC because we are going to modify PULP SoC and we add an additional IP to PULP SoC, our wide ywip. So let me open my modified IPs list of PULP SoC. That's this file here, right? Those are all the different dependencies of PULP SoC with one additional at the very bottom. ywip, the repository that I created myself. It's also on GitHub, that's why I didn't write a server, and it lives under the namespace of my personal GitHub account. So that's making wide ywip. Missing N over here. There it is. So those are the first steps. So you fork PULP SoC, fork it wherever you want. You modify the IPs list of PULP SoC to add the wide ywip as an additional dependency. You commit and push those changes. It's important that you push the changes since, as I always keep saying, when you modify the IPs list, you need to push it to the server. If you only modify the source files.yaml, regenerating the scripts, the Tickle scripts is enough. But IPs list changes need to be pushed to the server. So I committed those changes. I pushed them to my own fork of PULP SoC. And now the final steps, the step that maybe some of you forgot is we obviously also have to modify the reference of PULP SoC itself in the very top level of PULPIssimo. So now, instead of pointing to the version 2.0.0 of PULP SoC, I'm pointing to my very own branch, very own fork of PULP SoC. And again, I commit the changes, I push the changes, and I should be done. Now, sometimes stuff goes wrong, still goes wrong, although you already did the right steps to integrate the IP in update IPs. With time, you will get to know the quirks of the tool and know where to be careful about, but in doubt, it might always be a good idea if you think you integrated everything the right way to just clone your fork of PULPIssimo once again in a clean folder and run update IPs again. Then it will be forced to clone all the sub IPs according to the information in the IPs list. Because if you just modify an existing version of PULPIssimo and try update IPs, sometimes that fails because it doesn't alter the remote addresses of the sub IPs. And that's most of the time the reason why stuff goes haywire. Okay, after this rather long explanations. Are there any questions about the hardware part of the IP integration? Okay.
I have a question super fast. I see that you said that the ID width is super important, no?
Yes.
Could you please briefly explain which is the difference between the in and out width, and why the out width is fixed? It's like a parameter that we take from the package.
So where do you mean it is fixed?
Sorry. Okay, in the SOC, in the PULP sock.
Yes.
Okay. If you go into the declaration of the parameters,
yes,
I see that the axis ID out width is a local parameter, and it cannot be changed.
Yes. The reason for that is the following. If we have a look again at the interconnect structure, or SOC interconnect structure, there we are. Administrations, soft interconnect. So what we have for the ID width, the ID out width describes what's the ID width going to be for all the slaves that leave the AXI crossbar. And the AXI ID in width specifies what's the ID width of what enters the sock interconnect. So this is the block that comes from the cluster, right? Now, those two IDs should not have anything to do with each other because there is no AXI connection between this plug and this plug. It's first converted to TCDM and then back to AXI crossbar. Maybe trying to explain why that's important for the particular case of PULP Open is a bit more of a task for a face-to-face discussion, but has to do with that you should never connect two AXI crossbars with each other in both directions. That's what would be happening with the SOC and the PULP cluster, because PULP cluster also contains an AXI crossbar and you should not have a loop through both crossbars. Now, what is the ID width of the output? So the output ID width that leaves the crossbar is determined as follows. We go to the package sub interconnect over here. So that's the ID out width. So the right ID out width is determined by the number of masters. So the AXI crossbar, this IP over here, needs CLOC2 number of master ports as the minimum width of the ID. This is the number of bits that the AXI crossbar will add to the ID. So what I'm doing with this sock interconnect is that the TCDM to AXI4 converter down here, on this line, the ID has only a width of 1. It is only a single bit for the ID. That's this one over here. And the crossbar now adds a couple of additional bits. How many of them? Depends on how many masters you have. The more masters you have, the more bits of information you need in order to backroute the transactions. And I need exactly two number of master ports. So those are the number of master ports. But ID in width and ID out width should not depend on each other. I know that in an earlier version of the new sock interconnect, I did that the wrong way. I hope you were not confused by that when you had a look at it earlier, but they should not be related with each other.
No, makes super sense. Okay, thank you. Super clear.
Okay, any other question about the integration of the IP into PULP SOC? If not, then we come to the very part of this PULP training where Robert will briefly explain you what the steps would be to integrate to communicate with our newly integrated IP from the software side.
Okay, so as you maybe read in the exercise, the last part is writing a driver to talk to this accelerator we just integrated into the RTL. And for that, you were given the following files: divide alu driver file, divide alu driver header file, and the JSON description of the register map. So this is the JSON file. This is the JSON file which lists the whole register map. And let me show you. And this was the white alu driver C file, which has the implementation of all the driver functions. And finally, the white alu driver header. So I'm not going to solve the exercise here. So, but I'm rather going to tell what you were supposed to do by discussing the example solution. Okay. Let me open. Okay. So the first part was like doing the integration with the PULP runtime. And we already learned this in the previous exercises how we do this. We put the header files and the driver, the C body files in the correct folder, in the driver respectively in the include folder. Then we need to patch up the PULPIssimo make file to tell the PULP runtime about the new C files, and we need to tell pulp.h about the new header files. Let me show you. So on the right side, you see a file called runtime driver patch. This is the solution file, which shows you the difference. It shows you what you need to add to your file so that you get a working driver version. So we'll just, like Manuel, go over the solution. So in PULPIssimo make, we would need to add our driver implementation. You see, and yes, where was it? And in pulp.h, we will need to add our auto-generated header file, which we derive from the white alu JSON file, and our provided white alu driver header file. So these are the two steps to do the PULP runtime integration. What you still need is now also the base address of the IP. So when you run the rec tool, you will see that it will generate all the offsets of your registers, but it will not. Well, all these offsets are always relative to a. All these offsets are always relative to the base address, which is not defined. So you can see this here. This is the auto-generated file, and you see the base address is relative to this macro here, which you are supposed to define. In our case, it is this base address here. So this is also something you have to match with the address in the SOC interconnect. But in my case, I put it at 1A40000, and you can put this macro anywhere. But what makes most sense is that you put it in a file, called memory map, which basically only lists all the base addresses of your IP. So this makes sense from an organizational point of view. Okay, so this is the integration part. Now the implementation part that remains is from implementing these three functions and such that you can run. Let me open it. Such that you can run this main.c file and show do this multiplication of 3 and 5. Now, most of the information you have now to glean from the hardware implementation and from the JSON file. From the HJSON file, but I will not go like into details too much. But the idea is always the same. You have a function, for example, set operation. You check the timer HJSON file, what the meaning is of this register field, and then you do the implementation by referring to the macros that are being generated from the auto-generated header file. For example, in this case, set OP, this is a register that you can write into, and it sets the operation that is being done in your in the accelerator. Now, this is just a standard C stuff where you access a volatile register where you declare a variable that points to the address of the register, and you declare it to be volatile, and then you do the standard bit magic to shift the bit at the correct with the correct value at the correct position. So this is basically the set OP. The set trigger is an analog thing, is analogous how we do it. Maybe notable is that if you really want to write the correct version of this operation, you have to think about memory barriers, about compiler barriers. The problem is that technically, when you do volatile accesses in C speak, so in the C language, then the accesses can be reordered. So it could happen that the compiler thinks it's better to first access the data register instead of the control register. For example, in our case, it could be that you do a sequence where you first write operands and then you write the trigger register, which would trigger the operation of the accelerator. It could happen that the compiler thinks it should first trigger and then write the operands. So what you need to do to prevent this, you use a compiler barrier to tell them reordering through this barrier is not allowed. But this is a technicality. I saw this. This is very rare that this really happens. In our case, we actually in the GCC compiler we defined the CPU to be a standard 4-stage in order pipeline RISC-V core, and so the compiler will nearly never think that this is a good optimization. But it can happen. You will see like these kind of things in the, for example, in the Linux kernel, you will see these kind of statements when you with the macros they use to access register. Anyway, this is the trigger operation implementation, and finally, you're also supposed to write divide multiply function, which is then called in main. So the divide multiply accepts two parameters that define the operands of the operation. In our case, a 256-bit operation A and a 256-bit operation B, and writes the result into this result array. And again, you're supposed to implement these functions before and then use them in the divide multiply function. So you can see what we do here. We first check if we are in a good state. Then next we call the set operands functions that is already provided. We call the set OP function and set it to be a multiplication because we do a divide multiply. So, and this set OP is something we just implemented. Then we call trigger OP, which triggers the operation. And finally, we again call this pull down function, which pulls the register that reports the status of the accelerator. And finally, depending on the status we get, we can say we succeeded or we failed. Okay, so this is the whole driver. Are there any questions about the driver implementation, about how to integrate it into PULP runtime? Then feel free to ask now. Okay, in that case, I guess we can wrap things up slowly. So maybe we can go through some organizational point that remain. And
yeah, so this would be the right and time and last chance for you to ask any remaining questions that you might still have, if you still have the energy to actually ask them. Are there any open questions? If not, then that's pretty much it. It was that's the whole 2 days PULP training. I know was a bit long.
I have one question.
Yes, sure. Go ahead.
So in the code, in the C code, I could not understand why we are taking an array of 32.
32 times 32 should equal to 512. Am I mistaken?
32 times 8.
But we are
32.
Right.
We went 32. Maybe it's too much.
yes. So it means 2 to the power 10 it will be, so 1024. But we are actually using only
right.
zero.
No, you're right.
Actually, yes, that's wrong. Yes,
That's
you're
wrong.
That's
Yeah,
good.
you're
Yeah.
right. I'm a bit.
We were thinking in bits.
Yeah.
And bytes. So it's this is wrong.
And we are only accessing only zeroth means index of that array. Means is there a reason why we are declaring it like integer 32t and
The
a
reason
of
is because we are lazy.
Yeah, this is the main reason. I guess we would have discovered more edge cases if we actually used a bigger number. Yeah.
But I mean, the whole point of the exercise was about how you can integrate your own IP and how you can communicate with it. It is not the goal of this exercise to make good use of this unarguably very silly accelerator.
Okay. Okay. Thank you.
Okay. Yeah, we will update this.
And will we get the solution today or?
Yeah, we will point you to the solution branch, I guess.
Yes. Maybe we need to do smaller cleanups.
Yeah, we
yes.
need to do some cleanups, but we will provide you with the sample solution of both the memory layout modification exercise as well as the Oxy IP integration exercise after we did some cleanup.
Okay, thank you.
Any other question? If not, then I have only one last thing. We will, in a couple of minutes, send you by email, send you a link to a form where you could give us some feedback on the training. It was the first time we did it in this format with such a large crowd. We would be really grateful if you could give us a couple of minutes of your time to give us some feedback on what we could improve, what you thought was a good thing to do, and what could be improved on the exercise, and what your general impression on these 2 days of training was. I guess that's all of this, all about this PULP training. So I think we are done. If there are no more questions, I thank you very much for your attention, and yeah, enjoy your Christmas break for the ones that don't keep working next week.